Hi, it's time for another math easy solution. Turn discuss further into applications of integrals, and now look at further into probability, and now look at normal distributions, and more specifically the normal distribution function. Basically, many important random phenomena are modeled by a normal distribution, or as it described in earlier videos as using a bell curve. And examples are test scores on aptitude tests, heights, weights of individuals from a homogeneous population, for example, females or males. If you use both, because if you combine the weights, you might have a different type of function. You'll have generally taller males than females. And also annual rainfall in a given location, and a bunch of other examples. And I'll go over that normal distribution graph in a bit. Basically, this means that the probability density function of the random variable x is a member of the family of functions. So again, if it's modeled by normal distribution, the formula for the probability density function is, in later videos I'll go over the derivation of this. This equals to 1 over sigma square root 2 pi, I'll go over what sigma is in a bit, times by e to the power of negative x minus mu, which mu is the average, and then divided by, and then squared, and then divided by 2 sigma squared. And now we'll just box this out like that. Let's get a neater box. Alright, so this box is neat enough. And now where again u is the mean or average of this probability density function, and or the random variable x, and sigma is that's Greek letter or lowercase Greek letter sigma is the standard deviation of this. And basically this standard deviation is a measure of how spread out the values of x are from the bell-shaped graphs of the members of families in the figure below. I'll draw that in a bit. We see that for small values of sigma, the values of x are more clustered about the mean, whereas for larger values of sigma, the values of x are more spread out. So now basically, once you have that formula, the graphs are just models of that formula. So if you were to graph it out, let's say x, y, and this family function looks something like this. Let's draw a generic one like that. So this is the famous bell curve. Actually, this doesn't. Goes like that, and it keeps going down and down like that. Let's draw this. Let's draw it one more time as just more accurate. So it has to keep going down and down. And let's just say this has a sigma of equaling to 1. So if we had a smaller sigma, it would be more clustered about the mean. Let's say the average or the mean is this point right here. Call this mu. Let's go draw it a bigger line like that. So let's say we were to get a smaller sigma. For example, let's go with half instead of 1 equals to, let's say, 0.5. So it would be more clustered. Another general one would be looking like that. So it would be, again, more clustered about the mean, or basically a steeper graph like that. And this is for smaller values of sigma, say sigma equals half. And similarly, for bigger values of sigma, you're going to have more spread out graph, so something like this, like that. And this one, let's just say that sigma equals to 2. Now going further, so this model of this graph, basically statisticians, or just if you can as well, if you have a bunch of data, you could just approximate, or for them they have methods for using sets of data to again estimate or approximate mu, which is the average, and sigma, which is the standard deviation. So again, a lot of statistics is modeling and estimating from just a lot of data. And the factor 1 divided by sigma times square root of 2 pi, like over here, that is needed to make the function f a probability density function, meaning that the summation has to equal 1 under the curve, or the area under the curve needs to equal to 1, that this needs to be the average. And in fact, it can be verified using the methods of multivariable calculus that again, to make sure that it's a probability density function, like I explained in my earlier video on the introduction to probability. Basically, the full area underneath the curve needs to equal to 1. So you could, in later videos, I will prove this using multivariable calculus once I go into that. So the integral of 1 divided by sigma 2 pi e power of negative x minus mu squared over 2 sigma squared, and then dx, so that you're taking the derivative, the integral, this equals to 1. So, and I will prove this in later videos. And again, yeah, I will prove this formula here, and also that mu here is indeed the average, as well as how this whole standard deviation formula, or actually more accurately, how the normal distribution formula, yeah, I got mixed up a bit, was formulated in, and I'll do that in later videos, how formulated or derived. Let's make it a bit better to understand. Yeah, derived, and I'll do this all in later videos. Basically, I want to cover this introduction to this formula, because basically this formula is just a graph. Again, it's just a model. It looks like this. When you change the sigma or standard deviation, it gets more condensed or more spread out. And that's the whole idea here. I want to go introduction here, because I'll do another example or two on determining the probability when assuming normal distribution function, and also wanted to go over this because it's just an application of integrals, which I'm currently on that topic. And also, like stated before, this type of model is used in many different real world phenomena, just because it is pretty applicable, and it's pretty much a lot of random stuff appears in this type of form. And again, in later videos, stay tuned for those. I will go over this in more detail, as well as prove each of these formulas, and also how this whole standard or this normal distribution formula was derived. Anyways, all for today. Hopefully you'll learn. Like always, you can download these exact notes in the link below. And thanks for watching, and stay tuned for another math easy solution.